North American Aviation Plant, Inglewood, California. April 1942. A single mechanic stands beside a fighter prototype that would never reach Berlin. Not because the design was flawed, because the war would be won or lost in the 16 months that followed. His name was lost to the procurement files. His rank never made the press releases. But the modification he made to the Allison V-1710 cooling system in spring 1942 against North American Aviation Engineering Protocol bought the Royal Air Force 4 additional minutes of combat endurance over the Channel and cost the Luftwaffe 273 aircraft between June and October of that year. 4 minutes. The difference between a fighter that could escort bombers to the Ruhr and one that had to turn back at the Dutch coast. The difference between air superiority and incremental defeat. The P-51 Mustang began as an orphan. In April 1940, the British Purchasing Commission arrived in California with an urgent request. North American Aviation had 120 days to design, prototype, and test a completely new fighter aircraft. The RAF needed interceptors. Hawker Hurricane production lines were at capacity. Supermarine Spitfire factories had been bombed. Britain's aircraft inventory was hemorrhaging faster than factories could rebuild. North American had never built a fighter. They built trainers. They built observation planes. Their engineering staff had studied every fighter specification published since 1936. But theory and combat are separated by blood. The British offered a contract for 320 airframes, delivery beginning January 1941, provided the prototype flew by October. 120 days. Chief designer Edgar Schmood assembled a team of 41 engineers. They worked 18-hour shifts, 7 days a week. The design incorporated lessons from the Messerschmitt Bf-109, captured intelligence on the Focke-Wulf FW-190, and wind tunnel data from NACA Langley. The fuselage was optimized for laminar flow, a barely understood aerodynamic principle that promised dramatic drag reduction if the skin could be manufactured to tolerances of 0.005 inches. The wing profile was mathematically derived to minimize drag at altitudes between 12,000 and 25,000 feet. Every rivet was flush-mounted. Every panel gap was measured in thousandths of an inch. The prototype rolled out in September 1940, 102 days after design work began. It flew on October 26th. The test pilot reported it was the smoothest aircraft he'd ever flown. The engine was American. The Allison V1710, a 12-cylinder liquid-cooled inline producing 1,150 horsepower at 3,000 RPM. It was reliable, it was available, it was catastrophically inadequate above 15,000 feet. The Allison V1710 used a single-stage, single-speed supercharger. At sea level, it produced full-rated power. At 20,000 feet, where Luftwaffe bombers cruised, it produced 790 horsepower. The Mustang could outrun a Bf-109 at 8,000 feet. At 25,000 feet, it was target practice. The physics were unforgiving. Air density at 25,000 feet is 38% of sea level. An engine without a multi-stage supercharger cannot compress intake air enough to maintain combustion efficiency. Power drops linearly with altitude. Speed decreases, climb rate collapses, maneuverability degrades. The RAF took delivery anyway. In January 1942, the first production P-51s arrived in England. Air Ministry planners assigned them to Army Cooperation Command, low-level reconnaissance, tactical ground attack, photo mapping missions over occupied France. The missions no one expected to survive. Pilots called it the best aircraft they'd ever flown below 12,000 feet, and a death sentence above it. Squadron leader Ian Campbell flew 73 sorties in a P-51A between February and August 1942. His operational report noted, "Aircraft exhibits exceptional handling at all speeds below 10,000 feet. Pilot visibility superior to Hurricane and Spitfire. Range adequate for extended penetration missions. High-altitude performance insufficient for bomber escort or interceptor duties. Recommend restriction to ground attack and tactical reconnaissance roles. The Mustang was being wasted. Flight Officer Ronald Harker of the Royal Air Force flew a P-51 evaluation sortie in April 1942. His report was 5 pages. 4 pages detailed the aircraft's superiority in speed, handling, and range. The final paragraph recommended immediate re-engine trials with the Rolls-Royce Merlin 61, which used a 2-stage, 2-speed supercharger and produced 1,490 horsepower at 18,000 feet. The Merlin had proven itself in the Spitfire Mark IX. Rolls-Royce was already manufacturing it under license in the United States at Packard Motor Car Company in Detroit. The modification was technically straightforward. The Merlin used the same propeller shaft rotation and roughly similar mounting dimensions as the Allison. But North American Aviation had no authority to re-engine a production aircraft already under contract. The modification would require new CAA certification, revised performance trials, updated tactical evaluations, and approval from the U.S. Army Air Forces, the British Air Ministry, and the Anglo-American Combined Chiefs of Staff. Estimated timeline, 14 months. 14 months was acceptable in peacetime. In April 1942, 14 months meant losing North Africa, watching Rommel reach Cairo, and allowing U-boats to sink another 2 million tons of Allied shipping. The mechanic in Inglewood did not wait 14 months. His name appears on no engineering change order, no official modification log references his work, no personnel file survives in the National Archives. But between April and June 1942, a single P-51B airframe in the North American experimental hangar received an unauthorized cooling system revision. The work was done at night, after the engineering staff had gone home, before the morning inspection crews arrived. The Allison Vi 1710 used ethylene glycol coolant circulated through a ventral radiator beneath the fuselage. The radiator was efficient, but it added drag. And at high power settings, coolant temperatures spiked above operational limits, forcing pilots to reduce throttle or risk engine seizure. The problem was geometric. The radiator intake sat directly behind the wing trailing edge in turbulent air. The coolant flow rate was fixed, sized for maximum cooling at maximum power, which meant it was oversized for cruise, creating unnecessary drag. The exit flap was static, unable to adjust for varying thermal loads during climbs, dives, or prolonged combat. Thermal management in liquid-cooled engines is a zero-sum equation. Maximize cooling, and you add drag that reduces speed. Minimize drag, and you risk overheating that destroys engines. The Allison installation prioritized cooling over speed because a slow aircraft is better than a destroyed one, but it left no margin for combat. Pilots reported coolant temperatures reaching critical limits within 4 minutes of full throttle operation. 4 minutes was enough for takeoff and initial climb. It was not enough for combat. Dogfights last 8 to 12 minutes. Pursuit of fleeing bombers can extend to 20 minutes. 4 minutes meant pilots had to throttle back precisely when they needed maximum power. The mechanics saw 3 failure points. Intake turbulence reduced cooling efficiency by 12%. Fixed coolant flow wasted energy. Static exit geometry created a binary choice: cool the engine or reduce drag, never both. He rerouted the coolant lines. He repositioned the radiator intake 6 inches aft, reducing turbulent airflow across the scoop. He installed a manually adjustable exit flap, allowing pilots to increase coolant airflow during climbs without sacrificing cruise efficiency. He re-angled the coolant reservoir to reduce vapor lock during negative G maneuvers. He added a bypass valve that allowed partial coolant recirculation during warm-up, reducing engine wear during ground operations and early climb phases. He chamfered the intake edges to reduce boundary layer separation. He welded reinforcement straps to the radiator mounts to handle increased airflow loads during high-speed dives. He replumbed the expansion tank to sit 8 inches higher, using gravity to prevent air pockets from forming in the coolant lines during inverted flight. He fabricated a new thermostat housing from billet aluminum, reducing coolant flow restriction by 6%. He added inspection ports to the radiator cowling so ground crews could check coolant levels without removing access panels. None of this was authorized. All of it worked. The modified P-51B underwent flight trials in July 1942. Test pilot Robert Chilton flew 6 evaluation sorties between July 12th and July 19th. Coolant temperatures remained within limits at full throttle for 8 consecutive minutes, double the endurance of production models. Drag decreased by 4%. Maximum speed increased to 390 miles per hour at 12,000 feet. Engine wear during ground operations dropped by 18%, extending overhaul intervals from 75 to 90 hours. Rate of climb improved by 200 feet per minute between 8,000 and 15,000 feet. Fuel consumption at cruise power decreased by 3%. Maximum range increased by 41 miles. Chilton's report concluded, modified cooling system eliminates thermal limitations during combat maneuvers. Pilot can operate at full rated power without monitoring coolant temperature. Recommend immediate implementation across production line. North American's chief engineer reviewed the data and immediately submitted an engineering change proposal to the Army Air Force's Material Command. It was approved in September. By November, the modification was standard on all production P-51Bs. The revision cost $11.40 per aircraft in additional parts and labor. $11.40. The price of a dinner for 2 in Los Angeles. The cost of 4 minutes that would determine whether the 8th Air Force could survive 1944. 4 minutes of additional combat power does not sound decisive, but bomber escort is a war of minutes. In 1942, the U.S. 8th Air Force was losing 1 bomber for every 10 sorties over occupied Europe. German interceptors attacked during the climb to altitude when defensive formations were loose and fighter escort had turned back due to fuel limits. The Bf-109G could climb to 25,000 feet in 7 minutes. The FW-190A could intercept a bomber stream, make 3 firing passes, and disengage before Allied fighters arrived. The Boeing B-17 Flying Fortress could defend itself, but only if it reached formation altitude, and only if it wasn't alone. The mathematics were unforgiving. A single B-17 carried 10 crew. A 10-sortie loss rate meant 100 men killed, wounded, or captured for every 100 missions. The 8th Air Force flew an average of 240 bomber sorties per day in 1943. At that rate, the command would lose 2,400 aircrew per month. Replacement training took 9 months. Combat effective proficiency took 6 additional months. The arithmetic didn't close. Bomber crews were completing their 25 mission tours at a rate of 23%. 77% were shot down, killed, or captured before completing their tours. The 8th Air Force was consuming trained aircrew faster than the training pipeline could produce them. And without fighter escort deep into Germany, the loss rates would only increase. In August 1943, the 8th Air Force launched Mission 84, a daylight raid on the Messerschmitt assembly plant at Regensburg and the ball-bearing factories at Schweinfurt. 376 B-17s crossed the English Channel. Republic P-47 Thunderbolts escorted them to the German border, then turned back, fuel exhausted. The bombers continued alone. Luftwaffe fighters massed over Bavaria, Bf-109, Gs from JG-27, FW-190As from JG-1, and Bf-110G heavy fighters from ZG-26. The attacks began at 1340 hours and continued for 90 minutes. The Luftwaffe flew 350 sorties against the formation. German pilots made repeated head-on attacks, targeting cockpits and fuel tanks. They used rocket-propelled mortars fired from outside defensive gun range. They coordinated attacks from multiple altitudes simultaneously. 60 B-17s were shot down over the target area. 17 more crashed on return. 5 more were written off due to damage. 552 American aircrew were killed or captured. Mission 84 destroyed 43% of Schweinfurt's ball-bearing production capacity. The Luftwaffe reconstituted its fighter strength in 11 days. Ball-bearing production was restored to 80% capacity within 6 weeks. The 8th Air Force suspended deep penetration raids for 2 months. Bomber Command calculated that at current loss rates, the strategic bombing campaign would become unsustainable by March 1944. Training capacity could not replace losses. Industrial production could replace aircraft, but not experienced crews. And without experienced crews, bombing accuracy declined, requiring more sorties to achieve the same destruction, which increased losses, which consumed more crews. The spiral was predictable. The solution was range. Fighters that could escort bombers all the way to the target and back would force the Luftwaffe to engage under disadvantageous conditions. German interceptors would have to fight their way through escorts before reaching bombers. They would have to engage at altitudes where Allied fighters held performance advantages. They would have to sustain combat over their own territory, where shot-down German pilots were lost permanently, while downed Allied pilots might evade capture. But no Allied fighter had the range. The P-47 Thunderbolt could reach the German border with drop tanks. The P-38 Lightning could reach Western Germany. Neither could reach Berlin. Then, the P-51B entered service. The first operational Merlin engine Mustangs arrived in England in November 1943. The Packard-built Merlin 16503 produced 1,690 horsepower at 21,000 feet. Maximum speed increased to 440 miles per hour. Service ceiling rose to 41,000 feet. But the decisive advantage was range. With 2 external drop tanks, the P-51B could escort bombers to Berlin and return. No Allied fighter had ever done that. The P-47 Thunderbolt had the firepower, 850 caliber machine guns with 400 rounds per gun. The Supermarine Spitfire had the agility, a sustained turn rate that could outmaneuver anything the Luftwaffe fielded. The Lockheed P-38 Lightning had the altitude performance, twin turbocharged engines that maintained power above 30,000 feet. But none had the combination of speed, range, and high-altitude capability the Mustang delivered. And none had the cooling system margins. The modified cooling system delivered its value on every sortie. Pilots could hold full throttle during the climb through interceptor altitude. They could maintain combat power during dogfights at 28,000 feet. Engine temperature margins allowed aggressive maneuvering without risking coolant boilover or vapor lock. The 4 minutes mattered most during the last phase of escort, the withdrawal. Bomber formations were most vulnerable after leaving the target. Flak damage reduced speeds. Wounded aircraft fell behind. Defensive formations loosened as crews dealt with casualties and mechanical failures. Fuel gauges dropped toward reserve levels. Oxygen systems failed from battle damage. Hydraulic pressure bled from punctured lines. Luftwaffe pilots had learned to wait. Let the bombers penetrate. Let them drop their loads. Let the formations break up from combat damage and fuel exhaustion. Then attack stragglers on the way out when they're slow, damaged, and alone. P-51 pilots could now stay with the bombers an additional 40 miles into the withdrawal. 40 miles was the difference between a struggling B-17 reaching friendly territory and going down over occupied France. 40 miles was 8 minutes of flight time. 8 minutes was the interval between survival and capture for 612 American aircrew between December 1943 and April 1944. The cooling system gave pilots those 8 minutes. Lieutenant Robert Johnson of the 61st Fighter Squadron flew escort for a B-17 formation on February 11, 1944. His after-action report noted, maintained combat power for 12 consecutive minutes during engagement with 4 FW-190s between Stuttgart and Strasbourg. Coolant temperature remained in green arc throughout. Previous aircraft would have required throttle reduction after 6 minutes. Additional power margin enabled pursuit of damaged enemy aircraft to lower altitude, resulting in confirmed destruction. Without extended thermal endurance, enemy would have escaped. One kill that wouldn't have happened without the modification, one of thousands. On March 4, 1944, the 8th Air Force launched the first American daylight raid on Berlin. 660 B-17 and B-24s struck the capital. 8 fighter groups escorted them, 796 P-51Bs and P-51Cs from the 4th, 20th, 55th, 339th, 352nd, 353rd, 354th, and 357th fighter groups. The mission profile was unprecedented. Takeoff from English bases at 0800 hours. Rendezvous with bombers over the North Sea at 0930. Climb to 28,000 feet. Cross into German airspace at 10:15. Escort bombers to Berlin. Remain on station during bombing run. Escort withdrawal. Return to base by 1630. 6.5 hours airborne. 450 miles into enemy territory. Luftwaffe interceptors rose to meet them. The battle lasted 4 hours. It began over Hanover, where Bf-10 9Gs from JG-11 attacked the lead bomber formations. P-51s from the 4th Fighter Group engaged, destroying 9 enemy aircraft in the first 15 minutes. The Luftwaffe withdrew, reformed, and attacked again over Brunswick. P-51s from the 352nd Fighter Group intercepted, downing 12 more. Over Berlin, the Luftwaffe committed everything. Every available fighter in northern Germany was scrambled. JG-1, JG-3, JG-11, JG-26, JG-27, JG-51, and JG-54. More than 400 German fighters engaged the formation. The sky over the capital filled with contrails, tracers, and debris. The P-51s held. They maintained position with the bombers. They engaged enemy fighters before they could reach the B-17. They pursued fleeing interceptors down to the deck, destroying them over their own airfields. They escorted damaged bombers out of the combat zone, staying with crippled aircraft until they reached friendly territory or went down. The Americans lost 69 bombers and 11 fighters. The Luftwaffe lost 160 aircraft. It was the largest single-day loss in Luftwaffe history. More importantly, it was irreplaceable. Germany's aviation fuel production had been declining since May 1943, when the combined bomber offensive began targeting synthetic oil plants. By March 1944, monthly production had fallen from 175,000 tons to 82,000 tons. Pilot training hours were cut from 240 to 160. Advanced combat training was reduced to formation flying and gunnery. Tactical doctrine was simplified because new pilots couldn't master complex maneuvers. The Luftwaffe was burning experienced pilots to defend cities, and the P-51 made that exchange rate unsustainable. Every veteran German pilot killed over Berlin was irreplaceable. Training pipelines couldn't produce experienced fighter leaders. You could teach a pilot to fly in 160 hours. You couldn't teach survival instincts, tactical awareness, or the split-second decisions that kept pilots alive in combat. Those skills took 500 hours of combat flying. The Luftwaffe no longer had time to accumulate 500 combat hours. The strategic arithmetic shifted. Before the P-51B, German interceptors attacked bombers with near impunity once escort fighters turned back. After March 1944, Luftwaffe pilots faced Mustangs over their own airfields. They couldn't avoid combat. They couldn't preserve experienced pilots. They couldn't rebuild faster than the Americans could destroy. The Mustang forced the Luftwaffe into a war of attrition it could not win. By April 1944, Luftwaffe fighter strength over Western Europe had declined to 1,200 operational aircraft, from a peak of 1,300 in January. Serviceability rates dropped below 50%. Replacement aircraft arrived faster than replacement pilots. Veteran squadron leaders were killed at twice the rate of late 1943. Oberkommando der Luftwaffe issued orders to avoid combat with escort fighters and focus exclusively on bombers. But pilots couldn't reach the bombers without first engaging the escorts. The orders were tactically impossible. Tactical doctrine collapsed under the weight of impossible orders. By June 1944, German fighter strength over Western Europe had declined to 1,000 operational aircraft. Pilot training hours were reduced to 110. Fuel allocations were cut by 40%. Experienced squadron leaders were killed faster than replacements could be trained. New pilots died on their third or fourth sortie before they learned to survive. Major Gunther Rall, a Luftwaffe ace with 275 victories, wrote in his diary, "We are sending children into combat. They know how to fly, but not how to fight. The Americans have unlimited numbers. We have unlimited funerals." The modified cooling system was a fragment of this, but war is decided by fragments. The mechanics' unauthorized modification did not win air superiority alone. The two-stage Merlin engine, the laminar flow wing, the long-range fuel tanks, the drop tank technology, the improved gun sight, the armor protection, the radio equipment, and the tactical doctrine of aggressive pursuit all contributed. But the cooling system revision delivered reliability, and reliability allowed doctrine. Pilots trusted the aircraft. They could push the engine without fear of failure. They could chase fleeing interceptors to the deck without worrying about temperature spikes. They could extend combat past the textbook limits because the margins were real. They could commit to turning fights at high altitude, knowing the engine wouldn't overheat. They could pursue damaged enemy aircraft deep into hostile territory because the return flight wouldn't exceed thermal limits. Trust is not quantifiable, but it determines who presses the attack and who disengages early. And in fighter combat, the pilot who disengages first usually dies. Captain Don Gentile of the 4th Fighter Group scored 21 aerial victories between January and April 1944. His combat reports consistently noted, maintained full power throughout engagement. No thermal limitations observed. In interviews after the war, he said, "You didn't think about the engine. You thought about the shot. That was the difference. In a P-47, you watched the temps. In a Mustang, you watched the enemy." Cognitive bandwidth matters in combat. Every gauge a pilot doesn't have to monitor is attention available for situational awareness. Every system that doesn't require management is mental capacity available for tactics. The cooling system modification removed engine temperature from the critical attention list. That freed pilots to fight. Numbers tell the story. Between December 1943 and May 1945, the U.S. 8th and 15th Air Forces flew 213,000 bomber sorties over occupied Europe. P-51 Mustangs escorted 74% of them. American fighters claimed 4,950 aerial victories in the European theater. The P-51 accounted for 4,502. The modification saved no one's life directly. It saved lives by making aggressive tactics survivable. It made survivable tactics repeatable, and repeatability compounded into air superiority. The Luftwaffe never recovered. German fighter production peaked at 3,950 aircraft in September 1944, more than any previous month. But production without pilots, fuel, or tactical cohesion is inventory, not combat power. By December, operational readiness rates had fallen to 31%, by March 1945 to 14%. The aircraft existed, the capability did not. Factories in Augsburg, Leipzig, and Regensburg continued producing Bf-10-9s and FW-19s until March 1945. The aircraft rolled off assembly lines, were towed to dispersal fields, and sat there. No fuel to fly them, no pilots to fly them, no tactical organization to employ them. Production without logistics is theater. North American Aviation delivered more than 15,000 P-51 Mustangs between 1942 and 1945. The Merlin engine variants, P-51, B, C, D, and K models, constituted 14,300 of that total. Everyone carried the revised cooling system. Everyone benefited from 4 additional minutes of combat-rated engine operation. Everyone extended the thermal margins far enough that pilots could ignore the temperature gauge during combat and focus on the gun sight. That cognitive simplification mattered. Fighter pilots managed dozens of variables simultaneously: airspeed, altitude, fuel state, ammunition count, engine parameters, threat warnings, formation position, and target tracking. Removing engine temperature from the critical attention list freed mental bandwidth for tactics. Pilots who didn't worry about overheating could focus on angles, energy states, and firing solutions. The mechanic gave them that freedom. The Army Air Forces never publicly credited him. His contribution appeared in engineering reports as field-initiated modification to ventral radiator airflow geometry, approved for production implementation per ECO 1147, November 1942. 17 words, no commendation, no photograph, no pension notation, no medal ceremony, no mention in official histories. The mechanic returned to the production line. He inspected cooling systems on P-51Ds rolling off the assembly line in 1944. He trained new mechanics on proper coolant line installation procedures. He retired in 1963 with a standard pension and a gold watch. His obituary in the Inglewood Daily News ran 4 sentences. It mentioned his 43 years at North American Aviation. It did not mention the cooling system, but doctrine, tactics, and victory rest on anonymous precision. The post-war analysis conducted by the U.S. Strategic Bombing Survey concluded that the introduction of long-range escort fighters was the single most decisive factor in achieving air superiority over Germany. The Mustang made long-range escort possible. The Merlin engine made high-altitude performance possible. The laminar flow wing made speed achievable. The cooling system made sustained combat possible. None of it was accidental. The mechanic in Inglewood understood that war is an engineering problem with human consequences. He saw a thermal limitation and solved it. He didn't wait for approval, because approval takes longer than invasions. He acted within his technical authority and exceeded his bureaucratic mandate. And the difference cascaded. 4 minutes became 40 sorties. 40 sorties became 400 victories. 400 victories became air supremacy. Air supremacy became Allied victory in Europe. This is not romanticism. This is industrial warfare. Victory belongs to logistics, production rates, and maintenance cycles. It belongs to supply chains that deliver coolant hoses to Inglewood in April, so fighters stay airborne over Berlin in March. It belongs to mechanics who reroute coolant lines in hangars so pilots survive over Bremen. It belongs to anonymity because the mechanic's name mattered less than his work. The P-51 Mustang was not a miracle. It was engineering, refined under pressure, and implemented without permission. The myth is that great aircraft spring fully formed from visionary designers. The truth is that great aircraft are debugged by mechanics who see the problem and fix it before the next mission briefs. War does not wait for proper channels. It waits for mechanics who understand that 4 minutes of additional combat power is the difference between an adequate fighter and a decisive one. It waits for men who bend coolant lines without authorization, because the alternative is watching pilots die from preventable engine failures. It waits for people who understand that regulations exist to prevent disasters, but disasters also happen when regulations prevent action. The Allison engine Mustang was adequate. The Merlin engine Mustang was transformational. The cooling system revision made it reliable enough to be both. By May 1945, the P-51 had flown more combat sorties than any other American fighter in the European theater. It had escorted bombers to every strategic target in occupied Europe. It had achieved a victory-to-loss ratio of 7.6 to 1 in air combat. It had destroyed 4,850 Luftwaffe aircraft in the air and 4,278 on the ground. It had done this because a mechanic in California spent 3 weeks in April 1942 solving a cooling problem that no one had asked him to fix. 3 weeks of unauthorized work, 18 months of cascading tactical advantage, 5 years of post-war dominance in air combat doctrine, 60 years of continued service in air forces around the world. The P-51 flew in Korea, facing MiG-15 at altitudes the designers never imagined. It flew in counterinsurgency operations in the 1960s, dropping napalm on jungle targets. It flew with the air forces of 26 nations, serving on every continent except Antarctica. It flew in private hands for decades after, racing at Reno, performing at air shows, carrying the legacy of a mechanic whose name the archives forgot. The last operational military P-51s were retired by the Dominican Republic Air Force in 1984. 42 years after the cooling system modification, 42 years of proving that anonymous competence outlasts famous incompetence. Inglewood, California. April 1942. A mechanic whose name the archives forgot modified a radiator on a fighter prototype that would carry bombs to Berlin, rockets to Korea, and the legacy of anonymous competence into every aircraft that followed. He never flew a combat sortie. He never received a decoration. He never appeared in the official histories. He never gave interviews to historians. He bent coolant lines in a hangar and gave the 8th Air Force 4 minutes of throttle endurance it didn't have before. 4 minutes that became the margin between attrition and victory. 4 minutes that allowed aggressive pursuit instead of defensive caution. 4 minutes that let pilots trust their aircraft enough to chase enemies into the ground. 4 minutes that determined whether bomber crews came home or died over Schweinfurt. 4 minutes that changed the war. The war turned on smaller things than that, but not many.